Find the points on the graph of the function that are closest to the given point. F of x equals x squared, and the point I guess we're looking for is 0, 9. Okay, so we have f of x is equivalent to x squared. This creates a standard parabola shape, a standard upward facing parabola. I'm going to go ahead and sketch on the graph real quick, just a rudimentary sketch here. Not going to be real pretty, but here we go. It's basically going to be a parabola centered at 0 going upward like that, and then, kind of going upward like this way in the negative direction. Completely symmetrical, even though my drawing's not. But just imagine that this parabola is completely symmetrical across the y-axis, all right? The point in question is 0, 9. So that's the point we're looking for. I'm going to put that point here. So 0, if you count 0 on the x-axis, you have 0. You don't go left or right. You're just here. You just count up 9 units. And I'm going to say it's about here, okay? This is the point, 0, 9, all right? 0, comma 9. I'm actually going to write that a little bit out of the way. 1 second. I'm going to rewrite that. I'm going to do it up here. 0, comma 9. All right. So 0, comma 9. You are looking for the points that lie on the curve, that lie somewhere on this parabola that we just drew. You're looking for points on the curve that are closest to this point, 0, 9. And it's hard to do by graphing. I mean, you can do it's possible, but sometimes the function is really complicated. The method I'm about to show you will work for any function, any curve they give you. This will always work, no matter what the numbers are, the points, whatever. Graphically inspecting it, what would you say just by looking at it? Like, what if you had to move from this center point here to the curve? Which way would you move? Which way would be the quickest and shortest way? Would you move directly down to get to the curve? I would argue no, because you would have to move 9 units down. It's kind of a long way. To me, just by looking at it, it looks like the shortest distance to the curve, to either end of it, would be either to the left some unit or to the right some units. Let me change that. So I would say the shortest way is either to the right over here, going directly right, or going directly towards the left, because it is a parabola and it is symmetrical across the y-axis. So knowing that, I'm going to just basically draw an imaginary line that connects this point to the parabola here, right? I'm going to draw an imaginary, and this line is supposed to be flat with 0 slope, but it's basically, let me actually I think I get a line tool. Okay, cool. Let me try drawing that line again. I'm going to try drawing it that goes through this point, close enough, and boom, through that point. Line, it's not so important. This just helps us get a better visualization of what's the shortest route onto this parabola here, onto this curve. And so basically, knowing this, we can set up our equation, our little math equation. Because we're basically going directly out from either end, either to the left or right, we know that the y value on either end of this curve is going to share the same exact y value as our point here. And that y value is 9, right? If you move to the right, the y value doesn't change. The x value does, but the y value does not change. So immediately for your x smaller value and your x larger value, you know that the y value must share the same y value as the point on the curve. So this is for the small value, and then this one, same thing. We don't know what the x's are yet, but we know the larger value will also share the same y value, which is a positive 9 in this case. So how do we find these x's? Well, it's easy. And once we've identified what the y value is, we're going to plug it into the equation that was provided. Remember f of x? F of x is another way to write the letter y. It means the same thing. So I'm going to replace the f of x in the original equation with the letter y. I'm going to set it up as y equals x squared, right? I'm going to be using these y values here that we determined, this 9 y value, and I'm going to replace the y with the 9. So I'm going to say 9 equals x squared. Does that make sense? I hope so. In all three cases, oh, this is large. In all three cases, it's going to be 9. And so then you just solve for your x to find x. And how do you do that? Well, you take the square root of both sides, right? Take the square root. And so whenever you take a square root of a number, it cancels here. The square root and x squared cancel. But whenever you take a square root on the left, you need to insert this plus or minus to account for, both the negative numbers on the spectrum and the positive numbers on the spectrum that when you square them gives you this 9. So what's the square root of 9? Well, that's going to be a 3, and it's going to be a plus or minus 3. So this is what the x's are. And I bet you can tell me which ones are the small numbers and which one's the big one. The small one, of course, the small value is going to, of course, be the negative 3, comma 9, right? That's the small one. And then the larger one is going to be the positive 3, comma 9. And so what these points represent are these points up here on the graph. This is the negative 3, comma 9, and this is the positive 3, comma 9. And because it's x squared, you see it's symmetrical with the 3's. That's the shortest distance. That's like the closest points on the graph that lie to 0, 9. So this one is negative 3, comma 9, and this one is positive 3, comma 9, right? Let's call that 3. We'll call this one negative 3. And then this one up here is 9. Okay. And I hope that answers the question. Those are the point values. Just using a little, the process is just like kind of drawing out the graph and looking at, doing a little analyzing and drawing this imaginary like flat line with no slope through it. And after you do that, you realize, okay, I can like plug things in now and like solve for them. So that's like the secret. Thank you for watching. Ciao.